Hello, and thank you for the Cloud Threats and Vulnerability Summit's invitation to speak with you today. By this point in time, I've spent 5 full decades and a little more in some part or other of the software game. And the bigger fraction of that has been in the security field. But let me give you a little bit of advice. Whenever someone stands up and says, "Oh, I've been doing security for ever," the first words out of your mouth ought to be, "Well, if you've been doing security for that long, why haven't you fixed it by now?" That's a good question, and thank you for asking it. But for today, I'm going to try to fulfill the other challenge a long timeline should perhaps allow one to do, and that is to look at the position and the velocity of the field to see if knowing them helps make some predictions. In particular, as given by this talk's title, what might our software look like in the future? Although it is likely better to phrase that as, given the trajectory of software, what might our future look like? To get started, let's look for a bounded definition of software. Merriam-Webster has this definition: something used or associated with, and usually contrasted with, hardware, such as programs for a computer. Wikipedia has this definition: a set of computer programs and associated documentation and data. Encyclopedia Britannica has this definition: instructions that tell a computer what to do. ChatGPT has a different definition for every way you ask the question. And in a different historical context, Justice Potter Stewart said something that can be repurposed to the definition of software. I shall not today attempt further to define the kinds of material I understand to be embraced within that shorthand description, and perhaps I could never succeed in intelligibly doing so. But I know it when I see it. As we proceed here, do remember that once good definitions will change under the pressure of invention. Today's variety is expanding and its dispersion is deepening, thus giving rather a lot of relevance and scope to the title of this talk, Whither Software. In thinking about that question, we're not going to quote bundles of statistics here, though they are readily available and pretty amazing when you read them carefully. 2 foci probably ought to dominate our initial thinking on Whither software. One is edge computing, the other is cloud computing. Both of these also have loose definitions. IBM says edge computing processes data wherever it's created, while Google says cloud computing is the on-demand availability of computing resources over the internet. Those 2 definitions illustrate the inherently unstable pressure of invention. From where I sit, in versus out, central versus dispersed, edge versus cloud, and so forth, all exhibit a kind of oscillation when you look across the long term. 40 plus years ago, you would take your data to where the computing was, a university central computing facility perhaps. Then, inventions made it possible to move the computing to where the data was, and every worker came to have something on their desk called a workstation. with which to do that processing. Then came virtualization and the internet. So the distal end reverted to being primarily a display tool, while the data once again went to where the computing was. We are inside the next oscillation. Much computing is going back to where the data resides, that is to say, in the sensor fabric, per se. But now we have a coupled oscillator. Ubiquitous edge computing and omnipresent cloud computing. As you may recall from old physics or math classes, coupled oscillators are chaotic and are often aperiodic as well. So what does oscillatory behavior mean for our Whither software question? As it happens, the current oscillation back to moving computing to where the data is may be the last oscillation. Even if we wanted to do otherwise, computing has to go where the data is. Sensor cost is no longer a deterrent to deployment, and thus there's too much data to do anything other than moving computing to it. Noting also that the baseline driver for autonomy is likewise data volume. The wiggle room in these various definitions contributes to the difficulty of answering our question with any kind of satisfying precision. In artificially intelligent machine learning systems, we no longer have source code so much as we have source data. Whether we are talking the volume of data or talking the relevance of any given datum to some outcome. The systems that write or edit software make software into data per se. The leading natural language generators have over a half trillion, parameters. So what part of that is software and what part is data? Back to the definition of software. Do you in fact still know it when you see it? For the security of digital artifacts of any kind, we typically demand a chain of custody. If it turns out that an unknown somebody has been scribbling in the source code pool, we will declare a red alert. The most critical question in any supply chain attack is, how long has this been going on? The ability to answer the question of how long has this been going on rather depends on having source code control systems and good logs separated by a demising wall of some sort. The various newish attempts to certify a chain of custody via a software bill of materials runs into a restated form of the same problem. Is an annotated snapshot of the maker's source code control system good enough? Does such a snapshot provide sufficient provenance for an executable? Or do we need snapshots and provenance for the software build environment as well? What about build environments that include diversity compilers, where, in the name of security, every binary that is churned out is supposed to be different? Perhaps negotiating precise consensus definitions of software is rhetorical and just irrelevant. It is said that the most readily available prediction of tomorrow's weather is today's. That's a linear construct. But with software plus data, there's nothing linear anymore. It is all exponential. The compound annual growth rate of cloud computing is just under 20%. For edge computing in the form of the Internet of Things, the compound annual growth rate is 26%. Turning to security for the number of CVEs, it is just over 20%. Does that mean we're getting better at avoiding vulnerabilities? or that we are not discovering vulnerabilities fast enough? Is machine learning going to definitively answer the single great question of cybersecurity? Are vulnerabilities sparse or dense? Do we need to be negotiating the definition of vulnerability rather than the definition of software? Regardless, exponential growth of the attack surface means automation is essential, and thus we now have software reliability engineering, and we have algorithms deployed to protect us from other algorithms. Much as it has been roundly and publicly declared that the preferred cure for bad speech is yet more speech. Perhaps the dangers of an artificial intelligence can only be countered with yet more artificial intelligence. When I run some prosaic little software package on premises, and I do so offline, that is to say, in my home, for example, I know something about what is going on. When I do the opposite, that is to say, use a software as a service interface, there is nearly nothing I know, that is to say, really know, about what is going on, where the going on is taking place, or if either the going on, or the where are the same as they were yesterday. When I'm offline, I know that my copy is as good as it was, and it is all but surely the same as your copy. When I am online, I have no way to know if my results are what some other person's results are to the same problem. I might go so far as to say that full personalization of software environments is the enemy of trustworthiness, and for the very reason that there is no inherent comparability between my personalized experience and yours, or even between my experience today versus my experience tomorrow. Is the core differentiator between standalone software versus software as a service that for standalone software I have version control, but for software as a service I do not? Or is it more accurate to say that it is software if and only if I have a meaningful right to repair, and a service if I do not? Or is it software if and only if an examinable bill of materials is a meaningful construct in the particular case? Similarly, if the explainability problem in artificially intelligent machine learning really is insolvable, what does the word vulnerability then describe? Can we talk about provenance if we don't have crisp definitions? How might we think productively about this? Perhaps at some level of complexity, hiding behind a service interface has the effect of providing moving target defense, and for free. Certainly, security upgrades and the like are easier in a service model. Yet a service model also puts formal proofs of code correctness out of the reach of the user. Of course, if we're entering an age where the most important code is derived from data, then proving the correctness, the completeness, and the integrity of the ingested data all but surely supplants the goal of proving code correctness. And what about self-modifying software? Was 2021, say, last year when one might presume that everything you read online could be traced back to some human writer? If software is now distilled out of data, then what is the impact of putting software's output back on the internet to be strip mined by other datacom software. Looking from a different angle, digital systems are more brittle than analog systems. They contain no natural stasis to which they return when bumped. An off by one transient can cascade, while an off by a millivolt transient will be corrected by nature. Digital engineers must build sanity checks into their systems. Analog engineers need only build to tolerances. Digital systems keep themselves on point by checking against internally constructed norms. Analog systems are kept in equilibrium by external norms, that is to say, by the laws of physics. Initially, it would seem that brittleness is the Achilles heel of digital systems. If a system goes off the rails at the slightest touch, then life has been made a lot easier for an attacker who seeks to bring the system down. But at the same time, life is made much more difficult for the attacker who wishes to alter the behavior of the system silently. Off the rails is a sure sign that the system has been fiddled with. A design trade-off in constructing internal checks is therefore between system robustness, that is to say, against attacks to bring it down, and system correctness, that is to say, against attacks on its own functionality. The harder you make it to bring the system down, the easier you make it to alter the system undetected. As everybody gets spattered with mud when a system crashes, this trade-off is usually made, and without hesitation, in favor of more internal checks. Many, perhaps most, internal checks are against absolutes. If a denominator is 0, then the division is not performed. If the denominator is not supposed to be 0, then an error condition is raised. This brings the unexpected behavior of the system to the designer's attention, who can arrange for a considered response. The challenges of exception-based programming are widely recognized, but now that software is both massive and derived, the only place to test is in production. Suffice it to say that if the primary goal of the exception handling code is to fix up, to make good, and to press on, then you have made life a lot easier for the attacker who simply wants the system to misbehave from time to time. But what about another kind of internal check? One against relatives. Relative checks are against the system's own historic record. Has this person ever before purchased lingerie in Minsk? The exception is probabilistic rather than absolute, and the historic record is used to estimate that probability. If the exception raised by the check is highly likely, then it can be safely ignored, with, of course, the understanding that some risk has been incurred by doing so. If, on the other hand, the probability of the exception based on the historic record is low, then the exception is turned into an absolute exception, and the previous comment applies. It is in the matter of relative checks that the difference between digital and analog systems comes into stark relief. An analog system doesn't modify the criteria against which it checks itself as it operates. These are the laws of physics. They are both external to the system and inviolate. Relative checks of digital systems are, by contrast, against its own historic record, which record how the system changes as it runs. Should this historic record become slowly contaminated, decisions about what is and is not an exception to a relative check become quietly skewed. Synchronization primitives will ensure that a unitary change propagates. In the unlikely event that the contamination of the historic record is eventually recognized, there is little alternative to wiping the record clean and starting afresh. Once again, how long has this been going on? Which brings us to George Orwell. He who controls the past controls the future. Cautionary advice to the designers of digital system security, because it is also an invitation to those who would seek to ever so slowly and quietly change the trajectory of the system, or to divert it from time to time to their own use. If data stores are the replacement for source code repositories, then controlling the past, that is to say, controlling the data, controls the future. As you know, none of this is static. For desktops up through data centers, over time, cost stays constant, performance rises, and upgrades dominate. Out on the edge, over time, performance stays constant, costs go down, and devices proliferate. Ergo, the edge is making, or has made, the attack surface of the non-edge space trivial by comparison to the attack surface of edge computing. But is it still software if it has no remote management, no field upgrade capability, or does it effectively become hardware when the last of its firmware has been loaded? I submit that Whither software is not answerable with a single phrase, a single trendline graph, a single analytic paradigm. There's too much of it now, and in too many places, much less tomorrow. Like a rich ecosystem, speciation is proceeding, and those who would study software need to select a genus to study. If an ecosystem analogy is genuinely apt, then diversity of software species should be a source of resiliency. But as we have learned from ecology, there are species and then there are keystone species. In any type of ecosystem, a keystone species helps hold the whole thing together. Some ecosystems would not be able to adapt if their keystone species were to disappear. What sort of software is the keystone species in the ecosystem of edge and cloud computing, and everything else in between? Are we really lucky that there are 3 hyperscalers and not just one? Are hyperscalers the keystone species here? Or is it the open source pools that hold that role? The more you consider Whither software, the more you wonder whether the question can be answered, whether the present evolved state of software in and of itself has made prediction of software's future evolution unanswerable. Is this the well-known problem of trying to do prediction in the presence of a positive feedback loop? Can software's complexity pass a point where we no longer understand how it works? Clearly, the answer to that is yes, it can. Or speaking more cautiously, it is conservative risk management to act as if the answer is yes, it will. Do we need to know how something works to predict its future? Surely that is a yes answer, as it goes all the way back to Aristotle's definition of efficient cause. Human history turned a corner when we humans internalized the idea that effects had discoverable causes, and that we should put aside foretelling the future by way of divination and instead turn to methodically evaluating cause and effect, including making allowances for uncertainty. In his 1996 Harvard Business Review article, the late, great Peter Bernstein wrote that more than any other development, the quantification of risk defines the boundary between modern times and the rest of history. Putting Bernstein's thesis in its contrapositive form, ours is a primitive state wherever we are unable to quantify risk. And so it is with software. When Andrei Karpathy compares trained machine learning models, which he calls software 2.0, to software in its conventional sense, he observes that at the end of the training, we're left with large networks that work well, but it's very hard to tell how they work. That is to say that we are left with a choice of using a 90% accurate model we understand, or a 99% accurate model we don't. And that 2.0 stack can silently fail. I have frequently written that the paramount goal of security engineering is no silent failure. Not no failure, but no silent failure. I take that stand because I define a state of security as the absence of unmitigatable surprise. Not the absence of surprise, but the absence of unmitigatable surprise. And you cannot mitigate a failure you don't know is happening. If Karpathy is on the right track, then his description of a software environment in which we are left with a choice of using a 90% accurate model we understand or a 99% accurate model we don't would seem to imply that it is in the model we don't understand where silent failure is going to happen. In no small part because we are sure to apply software that is too complex to understand to problems that are too hard to otherwise evaluate. Already it is a commonplace that we don't edit source code, we edit the training data from which it was derived. Quoting a typical definition of computability theory, it studies which problems are computationally solvable using different models of computation. A central question of computer science is to address the limits of computing devices by understanding the problems we can use computers to solve. But what sort of disconnect is it when we can't tell how a computation does its magic? The answer there is probably not whether there exists any one human being who does, in fact, fathom how a large language model with 500 billion parameters produce some given result. Perhaps it is good enough to say that a given result can be explained, that it is only size that makes it impossible to do so in the general case, i.e. that there is no principled reason beyond size. But that's not very satisfying if your job is to make some software system better without ever knowing how it works its guarantees. Perhaps we have rederived the wisdom of Donald Knuth. Premature optimization is the root of all evil. Perhaps it is Michael Dell. Left to themselves, creative engineers will deliver the most complicated system they think they can debug. Or is it Secretary of State John Foster Dulles? The measure of success is not whether you have a hard problem to solve, but whether it is the same problem you had this time last year. Or maybe it is David Wheeler. All problems in computer science can be solved by another layer of indirection, except for the problem of too many layers of indirection, which immediately invokes Camille Paglia. The sweeping appeal to history somehow overlooks history's far darker lessons about the cyclic rise and fall of civilizations, which as they become more complex and interconnected, also become more vulnerable to collapse. The earth is littered with the ruins of empires that believed they were eternal. Whither software, indeed. There's never enough time. Thank you for yours.